So what is Dalton's law of partial pressures? Well, it just says that the total pressure in a system, if you have a mixture of gases, is just the sum of all the individual gas pressures. So P total equals like P1 for gas number 1 plus P2 for gas number 2, etc. So the idea here, the concept is that the total pressure just depends on the total moles of gas, not the identity of the gas. It doesn't matter what this gas is. It could be oxygen, it could be helium, it could be, something different. They don't have to be similar gases in their chemical properties, in their molar mass, or anything like that. What matters is just the total moles of gas when it comes to the total pressure. Okay. So here's a little illustration of this, which you have in your handout. And Dalton's law is either one of those things where you just kind of go, well, duh, because it's just very intuitive, or for some people really struggle with it, and I'll try and explain why I think that is when I'm talking about this picture. So, if we have two gases in separate containers, and if the first gas exerts a pressure of 1 atmosphere in its own container, and if the second gas exerts a pressure of 2 atmospheres in its own container, well, if we combine those two gases into the same container, as we've done over here, then the pressure is just going to be the total of the two individual separate pressures. Okay, so some people, I think, might believe that it's going to be, the same as maybe the highest pressure because it's in the same volume. And earlier we talked about how volume and pressure are related. Okay, but we also talked about Avogadro's law, which says that the pressure is also, and the volume are related to the number of moles of gas. So for some people, Dalton's law is really easy to comprehend, but for some people, they get really hung up on it. And I think it has to do with the volume aspect of it. All right, so having learned Dalton's law, we need to learn now this thing about the mole fraction before we can relate total pressure to individual pressures. So the mole fraction is just like it, the name kind of gives it away. It's a fraction based on moles. So for example, if I had a classroom full of students, I could do the fraction of students with brown eye color, right? I count the number of students with a brown eye color and I divide that by the number of students total, and I have the fraction of brown-eyed students, right? Well, the mole fraction is very simple.
Excuse me?
Because it's just that ratio of the number of moles of one component of a mixture to the total number of moles in a mixture, okay? The ratio of the number of moles of a component in a mixture to the total number of moles in a mixture. So a way to represent that with an equation. Oh, and by the way, it looks like a capital X, but and I guess you could call it capital X if you want to, but it really is supposed to be a capital Greek letter chi, like, we're college, we have an association with a college, right? So all the frats and sororities use the Greek letter. So we should know that, right? So this is, technically speaking, Greek letter chi. All right, and this, for whatever reason, that's the symbol that's used for mole fraction. So the mole fraction of some gas, I just represents, an individual gas. It's just going to be the number of moles of that individual gas divided by the total number of moles. And that depends on how many, components you have in your mixture. You could have 100, but the mole fraction is just the number of moles of that individual gas divided by the total number of moles. All right, so that's just a sort of a bare bones equation on what mole fraction means, but now let's relate it to Dalton's law and to pressure. And here's the equation. So if you want to know the partial pressure in a system due to an individual gas, it's just equal to the mole fraction times the total pressure. Okay, that's all there is to it. And this equation is on your equation sheet. Again, you just need to know how to use it, when to use it, but that's the key, okay? The individual gas pressures are related to the total pressure by the mole fraction. The mole fraction times the total pressure is going to be the partial pressure from that individual gas. Okay, so here's an example, and this example actually is going to give us a little bit of a review of doing, moles and Avogadro's number and things like that. So it says we have a flask that contains 0.030 moles of N2, 0.150 grams of O2, and 4 times 10 to the 21 molecules of NH3. We want to calculate the mole fraction of each gas. Okay, so really what I need to do first of all is I need to calculate the moles of each gas. So the moles of N2, I'm already given that. It's 0.030 moles. So I'm just going to do the moles of oxygen again. Moles of oxygen. So we've got 0.150 grams of O2 times 1 mole of O2 is 32 grams of O2 equals, I'll look at my calculator, 0.00469. 0.00469 moles of O2, okay? And then I have the 0.030 moles of N2. And so now I need to calculate the moles of NH3. So the moles of NH3 is going to be based on a number of molecules. So 4 times 10 to the 21 NH3 molecules times, and I'm going to use Avogadro's number to convert that into moles. Avogadro's number says that 1 mole of ammonia is 6.022 times 10 to the 23rd ammonia molecules. Okay, so I can calculate that. So I'm going to do that for exponent 21 divided by 6.022 to the 23rd times 10 to the 23rd equals 0.00664. 0.00664, okay? And so then the total moles, so the total number of moles is just going to be 0.030 plus 0.00469 plus 0.00664. Okay, you just add all those together to get the total number of moles. So plus 0.00469 plus 0.03. Okay, so if I did this math correctly, and there's a partial chance that I did not, well, the total number of moles would just be 0.0413. Okay, now again, using my sig fig rules, I can only go out to that place, right? Because that's I'm adding numbers together, and that's the one with the fewest digits past 0. Okay, so then to calculate the mole fraction of each of these, so to calculate the mole fraction of N2, I'm just going to go 0.03 and divide that by the total number of moles, which is 0.041. Oops, that's the wrong symbol. So that's the mole fraction. So then the mole fraction of O2 would just be 0.00, and I have to round, I guess. No, because this one I can just use the number as it's given. 0.00469 divided by the total 0.041, and then you do the same thing for the ammonia, the NH3. Okay, so that's 0.00664, and I divide that by the total 0.041. Okay, and so I'll let PowerPoint finish up that calculation. Erase all that. Go back to the arrow. Okay, so did I do that right? Yep, looks like I did. Got the right number of moles for each one. So then you just add them all together to get the total number of moles. And then to get the mole fraction, you just divide each individual number of moles by the total, and then that gives you the mole fraction. And by the way, all these should add up to 1. All your mole fractions should add up to 1. Okay, so that's just an example on calculating mole fractions. You want to get kind of comfortable with that. So here's another example where we use the mole fraction in a Dalton's law kind of application. So it says a mixture of helium and neon at a total pressure of 0.95 atmosphere is found to contain 0.32 moles of helium and 0.56 moles of neon. And it asks for the partial pressure of the neon, okay? Well, okay, so the equation that you want to write down first here is that the partial pressure, in this case of neon, is just going to be equal to the mole fraction of the neon times the total pressure. Okay, I'm given the total pressure is 0.95. So what I need to find is that mole fraction of neon. Well, the mole fraction of the neon is just defined as the number of moles of neon divided by the number of total moles, total number of moles. Okay, well, moles of neon I'm given is 0.56. Okay, and then the total number of moles would just be the two added together, so 0.32 plus 0.56. Okay, so that will allow me to calculate the mole fraction, and then once I get that mole fraction, I'm just going to multiply that times the total pressure, so multiply that times 0.95 atmospheres, and then that will give me the partial pressure of the neon. Okay, so I'll erase that and let PowerPoint finish it up. Oops. Okay, so total number of moles is just the moles of helium plus moles of neon, so you can add those together to get 0.88. And so that means that the mole fraction of the neon is going to be the number of moles of neon divided by the total number of moles. So 0.56 divided by 0.88 equals 0.63. And so, oops. So now I just use that 0.63 in this equation for relating the partial pressure of a gas to the total pressure of the system. Okay, that mole fraction of the neon is going to go right there. And then I multiply that times the total pressure which I'm given, and you get 0.6 atmospheres. Okay? All right, so those are the kind of questions that you could be asked about Dalton's law. And so I've got a Chem 101 activity for you. So go ahead and get that app ready while I tab over and open it up for you. This will be 4A, which you should be able to start now. So the first thing to do, there's a lot of different places you could start, but might as well just start in calculating the total number of moles of each gas you have in this mixture. So the moles of O2 plus the moles of methane plus the moles of neon. So you're given all those numbers, so you just add them up and you get 1.78 moles. And you are asked to find the partial pressure of neon. So now what you're going to do is you're going to use the moles of neon and the total number of moles to get the mole fraction of neon. So the mole fraction of the neon is just the moles of neon over the total number of moles. So it comes out to be 0.42. All right, and so then, you're just going to use that mole fraction and the total pressure to determine what the partial pressure of the neon is with this equation. So the partial pressure of the neon is just the mole fraction of neon times the total pressure. So you just, multiply those two numbers together and you get the answer. And it didn't specify whether it wanted it in, units of atmospheres or millimeters mercury or torr. So you could have just left it with millimeters mercury. But be aware of that. Sometimes the question might expect it in units of atmospheres, and then you'd have to do a unit conversion. All right, so good job. Okay, so now we want to focus really on one particular application of Dalton's law of partial pressures, and that is water vapor. Because anytime you have let's say this is a glass of water, so you've got the liquid water, right? Well, some of those water molecules are going to have enough energy to kind of jump out of the liquid phase and become gaseous phase water molecules, water vapor, right? So hovering over the surface of any body of water, as small as a drop or as big as the ocean, any volume of water hovering over the surface of that, you're going to have some H2O molecules in the gaseous phase. So if it's open to the atmosphere, then what you have right here hovering over the surface of that water is a mixture of gases.
Wow.
Okay, so you've got nitrogen there from the atmosphere, you've got oxygen there from the atmosphere, and you've got the water there that's from just the natural evaporation of water off the surface. And then, of course, there's other gases that are there in trace amounts. And so if you wanted to apply Dalton's law of partial pressures, then you could say that the total pressure right there hovering over the surface of that water would be the partial pressure of the oxygen plus the partial pressure of the nitrogen plus what we call the vapor pressure. That's a special term for it, vapor pressure, and then just the partial pressure of those other trace gases if you want to include those. Okay, so that vapor pressure, that water vapor pressure, is something that it's because we have to deal with it all the time. Folks have gone into the lab and figured out what it is at different temperatures because it is temperature dependent. Again, because those water molecules will have an amount, the average kinetic energy of those water molecules is related to their temperature. Okay, the higher the temperature, the higher the average kinetic energy those water molecules have. And so that's why there are higher vapor pressures at higher temperatures. But the bottom line is that these have already been determined. So if you know the temperature and you have a table, or these days just Google, then you can just find what that vapor pressure is. And the reason why you need it is because many times in an experiment, you have to account for that. You have to subtract it out, right? So, for example, and this was the scenario that was posed to you in the pre-class assignment, right? You're doing a collection of a gas by displacing water. So you have a reaction like that. So you have a reaction where a solid piece of zinc is dropped in hydrochloric acid in this test tube. Okay, well, that creates hydrogen gas. So the two products are zinc chloride and hydrogen gas. Well, that hydrogen gas is funneled through this tube and then into this jar right here where it's displacing the water. Before the experiment started, this thing was full of water, liquid water. But as I create that hydrogen gas, the hydrogen pushes the water down and out. and the hydrogen gas collects at the top, okay? But it's not purely hydrogen gas. You're not collecting only hydrogen gas in here because you've got this liquid water. So some of those liquid water molecules will have enough energy to be gaseous water molecules. Okay, so you're going to have two in this space right here that you're collecting the gas that you're producing. You're really going to have two gases. You're going to have hydrogen gas that you're producing from the reaction, and you're going to have the vapor pressure, the water molecules in the gaseous phase. So those are the two, significant gases in this mixture. So the other thing that's important to recognize is that the pressure of the gases in this space right here is going to be equal to the atmospheric pressure. Whatever the pressure is on the outside of the jar is going to be equal to the pressure inside this jar, because they're going to be sort of pushing against each other with an equal force until they find that balance, because you've got the atmospheric pressure trying to push the water into that jar, but you've got the pressure from the gases that you're collecting trying to push the water out of that jar. So it stops doing that. It achieves balance when the pressure inside the jar is the same as the pressure outside the jar. Okay, so that's what it says in this bullet right here. The pressure inside the jar, which we'll call total pressure, is the same as or equals the atmospheric pressure. And that's nice because I can just use an instrument, a barometer, or I can go to the internet or a weather report or whatever to get that atmospheric pressure. And the two of them are the same. Okay, so the atmospheric pressure is equal to the total pressure inside that space in the jar. And I know that that is the sum of two partial pressures. The sum of, the pressure for the hydrogen gas that I'm generating from the reaction, but also a little bit of pressure from the water vapor that's present simply because I have water present. Anytime you have water present, you're going to have water vapor present. Okay, so the other thing that I need to do, for example, if I want to calculate how many moles of hydrogen I've actually generated, is you have to go to a table and you have to look up this number and subtract it out. And so that's what this example problem is all about. It's a different reaction, but it's the same concept. So in this example, what we've done is we've taken this ionic compound, potassium chlorate, and we're heating it. And what happens is it decomposes and it produces oxygen when it decomposes. And so we collect that oxygen with the same kind of apparatus you saw on the previous slide and in the video. So we collect that at 25 degrees Celsius. And then we measured the volume of the gas that we collected. It turns out to be 229 mils. And we looked up in a barometer or from the weather report online or something. We found out that the atmospheric pressure is 754 torr, or millimeters mercury. Same thing, right? So the question is, how many moles of oxygen are formed? Okay, so let me just write some of this out and then we'll go through it in the PowerPoint. So the reaction that's occurring is the potassium chlorate. When you heat it up, it decomposes. And so one of the products is potassium chloride, okay, and the other product is O2 gas. And so I'm not going to balance this. This is unbalanced. We just, I don't want to take up too much time to balance it. But the key is that, you're getting oxygen gas. And so remember that what we want to know is how many moles of oxygen. Okay, so how many moles of that gas? Well, remember, PV equals nRT. And so I can rearrange that and solve for moles. So the moles of oxygen, the moles of O2 are going to be equal to the pressure of O2 times the volume of the O2 divided by R divided by the temperature. Okay, well, here's where we have to kind of focus our efforts, because the pressure of the O2, so remember that the total pressure is equal to that 754 torr. It's equal to the atmospheric pressure. So 754 torr. But that's equal to a pressure from the oxygen that I produce, but it's also got some vapor pressure in there. So I need to look this up. I need to look that up in a table based on the temperature, okay? So the table is going to give you different pressures for different temperatures. And so I need to subtract that out of the 754 to come up with the pressure of the oxygen. And so once you get the pressure of the oxygen, you plug it into the equation there. The volume is the 229 mils. R, we know, 0.08206 liter atmospheres per mole Kelvin. And then the temperature, we just need to convert that into Kelvin. So you got the 25 plus 273, and so that equals 298. Okay, so that's kind of the procedure that we're going to go through to solve this problem. Okay, so now I'll erase all that and I'll show it to you in PowerPoint. Okay, so we're going to correct for the partial pressure of water first, I guess. So, you know, the total pressure is 754, and so I need to subtract out that vapor pressure, which is something that I look up in a table, or, you know, Google it on the internet or whatever, and it turns out that at 25 degrees, it's 23.8. So you subtract those two numbers, and you get a pressure of 730.2 torr. Now, if we're going to use the ideal gas law, I need to convert that into atmospheres. Remember that the ideal gas law has that constant R, and that constant R has units of atmospheres in it, liter atmospheres per mole Kelvin. So I do need to convert that into atmospheres. So that's easy. You just use your conversion factor. The 1 atmosphere is 760 torr. Torr cancel. And so you get 0.961 atmospheres. Okay. So then you just rearrange your ideal gas law, the PV equals nRT. You rearrange it for moles because that's what you're asked to find.
Alrighty then.
And you use the pressure of the oxygen, which we just determined, the volume we're given, and that needs to be converted into liters as well. You can't leave it as milliliters. And then we use R, and we use temperature in Kelvin. So I you know, inadvertently kind of skipped a couple important steps when I hand wrote it out. I didn't convert into atmospheres, and I didn't convert into liters, and I should have mentioned that. So don't neglect to do that. Okay, but that answers the question. That's how many moles of oxygen were collected in this particular experiment. All right, so moving on to the next topic. So we finished Dalton's law of partial pressures. Now we want to talk about the theoretical basis for all of those named gas law: Boyle's law, Charles' law, Hamilton's law, Avogadro's law, Dalton's law. You know, those laws describe behavior, but this thing called kinetic molecular theory kind of explains why we have that behavior. But it does have certain assumptions that go along with it to make the explanation reasonable. So the first one is that gas atoms or gas molecules have a tiny volume compared with the collective volume that they occupy. You could even, if you didn't want to use the word tiny and you want to use the word negligible or insignificant, you could. They're so small compared to the space that they are in. No matter what that space is, they're so small compared to that space that it's essentially a negligible volume. All right, so assumption number 2, gases move constantly and randomly. Okay, they're not at rest. 3, they have an average kinetic energy that is proportional to absolute temperature. We've kind of already talked about that. So higher temperatures means higher energy, lower temperatures, lower energy. And that energy is exchanged in what we call an elastic way whenever they collide, either with the surface of the container or with each other. So that's assumption number 4, engage in elastic collisions with walls of the container and other gas molecules. Sorry. So what does that mean by elastic collisions? Well, that's a collision where there's no energy that's lost due to like sound. Like you hear two things collide together and you hear like a crash or a boom. Then that means some of the energy that went into that collision was released in the form of that sound energy, and it wasn't conserved in the collision itself. Well, we're assuming that that doesn't happen when gas molecules collide, that all of their collisions completely conserve energy. Okay. And then the last one is that gas molecules act independently of other gas molecules. I mean, it's not wrong to say that one gas molecule thinks it's alone in the universe. It has no idea that there are other gas molecules, and that goes back to rule number 1. They're so tiny in their space that they, practically speaking, never encounter another gas molecule. It's only randomly that happens. Okay, so now let's talk about how the kinetic molecular theory explains all of the behaviors that we learned in these gas laws. So first of all, those that involve pressure and volume. The first one was Boyle's law. We said the pressure was inversely proportional to volume, or so if pressure goes up, volume goes down, or if volume goes down, pressure goes up, right? So this is how we explain that. If you decrease the volume, you're going to increase the number of collisions. And we said at the beginning of this chapter that pressure is proportional to collisions, or pressure is kind of an indicator of the number of collisions with the surface of the container. So if I decrease the volume, We have more bounces, we have more collisions, so that means the pressure is going to go up. Okay, well, what about the one we just learned, Dalton's law? Okay, well, what we learned there was that it doesn't really matter what the identity of the gas is. It only matters how many gas molecules you have. So moles of gas. So the total pressure depends only on the total number of moles of gas, not on their identities. All right, and again, it just goes back to those assumptions that we listed in the previous slide. If it did depend on their identity, like their properties as individual gases, then I couldn't make a couple of those assumptions in the previous slide. Okay, Avogadro's law, very similar. So if we increase the number of moles, it increases the number of collisions. And so it's going to either expand to a larger volume to keep the pressure constant, or if we somehow maintain the pressure, maintain a certain volume, then we get into Boyle's law territory and the pressure goes, or pardon me, Avogadro's law, and the pressure goes up. Okay, so Charles' law. So now we're going to talk about how kinetic molecular theory applies to the gas laws that involve temperature. So Charles' law says that the volume and temperature are proportional. If one goes up, the other goes up. And this was pretty intuitive. You know, the idea that if I increase the temperature, then I'm increasing the energy of these gas molecules. So they're going to bounce around faster. And so their collisions, there are going to be more collisions in a given amount of time. Those collisions are going to occur with more force. And so that's going to expand the balloon if given the opportunity. Okay, or Amundsen's law, if they're not allowed to expand, then it's just going to increase the pressure. So increasing the temperature will increase the force of collisions if the volume is kept constant, and so pressure will increase. Okay. All right, so a lot of this we already kind of talked about before, but we just didn't give it a name, and I guess now we're giving it a name. All of those explanations is what we call the kinetic molecular theory of gases and their behavior. Okay, and so again, here's just some pictures that kind of illustrate what we're talking about. It doesn't cover all of the laws that we just went over, but it covers 3 of them: Amundsen's, Boyle's, and Avogadro's. But you know, Amundsen's law says that pressure is going to go up if we increase the temperature, and that kind of makes sense because if we heat it up, these gas molecules are going to bounce around faster with more force, so we'll have more collisions with greater force, so that's a higher pressure. Boyle's law: if I push that piston down and give that gas a smaller space to bounce around in, then there will be more collisions with the surface of the container. So pressure is an indication of the number of collisions. So since there are more collisions, that'll have a higher pressure. And then Avogadro's law, so I have a certain amount of gas, but then if you count gas molecules left versus right, on the right here, there's more gas molecules. So I increased the amount of gas that was in the container. And the reason why the piston went up is because there's that relationship between the volume occupied and the number of moles. And again, that's because of all those collisions are going to increase the pressure, which if the container is allowed to expand, then it will cause that container to expand its volume. Okay, so that's the kinetic molecular theory in a nutshell. And so now I'll give you another Chem 101 question to answer about that. So you should be able to start 4B now.